um, two classical interprocess communication problems. Dining philosophers problem. Okay, the first one. Okay. When we say dining philosophers problem, the problem has nothing to do with dining, food, okay, gastronomy. It is all about computer science. It doesn't have anything to do with the philosophers. Okay. So philosophers are processes. Okay. So this is process number one, process number two, process number three, process number four, and process number five. That's why since this is P, they had chosen this philosophers just to make the first letter the same. And these forks are for the resources. So this is resource number one, resource number two, resource number three, resource number four, and resource number five. In order for a philosopher to eat, this philosopher needs this fork and this fork. Without having these two forks, the philosophers cannot eat his food. Okay? And the same is valid for the philosopher number two and for all the philosophers. So each philosopher to be able to eat, they need two forks. And if we think in terms of processes, each process to be able to run, they need two resources. This P3 needs R2 and R3. This P5 needs, okay, R4 and R5, etc. Okay, so that's the idea. And since they have to share these resources, okay, think about these resources as global variables, okay? P1 cannot continue without having access to a global variable R5 and R1. But while P1 is using R5, P5 cannot use it because P1 is modifying it. And if both of them modify the same variable at the same time, that would cause loss of race conditions. That's not good. So P1, before starting working, it needs to get a lock on R1 and R5. So that's it. Okay. So this is what we mean. So there are five processes and there are five global variables, if you like to think it that way. Okay. If you like to think it that way. Five processes and five global variables. And for each process to run, P1 needs these two global variables. And P5 needs these two global variables. And they need exclusive rights, exclusive usage permissions for these variables. Okay, question. How many processes can work at the same time without causing any race conditions? How many processes can work at the same time?
Two non-adjacent processes.
So how many? Just give me a number.
Two. İki.
Two and iki they are both correct. If P1 works, these two cannot work, right? So either this one or this one is going to work. These two cannot work at the same time. So it looks like only two of them can work. Okay, it looks like only two of them can work at the same time. And we need to find a automated way of handling this. Okay, and let's look at our first solution. The solution is this. For each philosopher, there are five philosophers. Okay, for each philosopher, it says that I need philosopher number I. In order for this philosopher to work in a while loop, what do the philosophers do? They think, and when they get hungry, okay, they take the forks and they eat, and then after they are done, after they are full, they put their forks. So what does the processes do? They produce some data, okay, and they take the resources, then they put the data in necessary places and they release those resources. Okay, this is what we do. So process number one thinks or the philosopher number 1 thinks. It takes the fork number 1, and then it takes the fork number 2, and if it cannot take fork number 1, it blocks. Okay, so take fork is like a mutex. Okay, it takes fork number 1, then it takes it, otherwise it blocks. If it takes fork number 2, it takes it, otherwise it blocks. By the way, I think I made a mistake. I think process number 1. Oh, okay, yeah, okay. This is, yeah, these are all wrong. These are all wrong. Oh, come on. What is going on? I cannot. Okay. This doesn't write. This doesn't write. This thing. I don't know what is going on. I will start my application. I will restart it. Maybe start it from here. Number 2. Yeah. Okay. Draw board. So I numbered them in a wrong way. I think around process 1 there should be resource 1 and resource 2. I think I did it R1 and R5. That was not correct. By the way, today you are going to have your second quiz. Your second quiz is going to start at 12, okay, 12:30, and it will end at 12:40. Okay, so you will have your second quiz. So let other people know. There are 98 people now. So I think that number is going to exceed 120 when this quiz starts. Okay. So let me mark them right. For P1 it is R1, R2, R3, R4, and R5. Okay, so P1 needs R1 and R2. In this case, P1 needs, okay, R1 and R2, those two forks. Okay, then eats. If it can get it, okay, the process 1, then it will eat, and when it is done, it will release those mutexes. Okay, good. All 4 of them or 5 of them are running the same code. Of course, as always, our first try is never correct. There is a problem with this. Can you tell me what the problem is with this code? If you think about, everybody is running the same code, all the 5 philosophers. All the 5 philosophers are running the same code. What would be the problem?
None of them work, maybe, if we don't give resources right.
Well, I mean, if process number 1 starts working, takes the fork, eats, and it is eating, and the process 2 starts running, and while the process 1 is eating, okay, process 2 starts running, and it cannot take the fork number 2 because it is taken by process number 1. It will block, so it works. And process number 3 can take the fork number 3 and 4, and it's going to work. Yeah, so it works. So if the ordering is right, everything works. But tell me the ordering where it causes a problem. Tell me the
If a context switch happened between both taking the both forks, so between taking fork I and I plus 1.
yeah. If process switch happens here between those two forks, okay, take fork number 1 I and take fork number I plus 1. If you are unlucky and if the process switch happens there for all the processes, each one will get, for example, P1 took P1 took R1. Okay, it took it. Process switch happened. P2 took R2, and process switch happened. P3 took R3, and P4 took R4, and P5 took R5. And then they are all waiting something. Okay, the switch happened again. Switch happened again. R1 cannot continue because R1 cannot get R1. Sorry, P1 cannot continue because P1 cannot get R2. P2 cannot continue because it cannot take R2, etc. So there is a deadlock. They cannot continue. Each one is waiting for each other, and this is not a good thing. Okay, so there is a potential problem with this code. There is a potential problem with this code. It can cause deadlocks if we do it this way. Okay, so somebody had offered a solution, a general solution. By the way, if I take the forks in order, for example, this is the order of forks being taken. Take the fork number 1 first, then 2, then 3, then 4, then 5. This is the order always. If I follow this order, then you might say that I am using in that order. This is not in that order, right? 1, 2, 3, 4, 5, 5. Okay. This is the order of the resource allocations. If I follow this order always, there will not be any deadlocks. Well, you might say that I always do that, okay? Take fork number 1, then fork number 2. For process number 1, it is okay. It takes fork number 1 and 2. Process 2, it is okay. 4 is okay. But for process number 5, the things are different. Why? Because it takes fork number 5 and it takes fork number 1. So it changes the order. It should take the number 1 and number 5. Okay? You understand it? We can solve this problem if I can order these fork allocation sequence. Okay? Maybe we can solve it that way. But this solution is not a very general solution. Why? Because before you begin taking all the forks, you need to know how many forks you are going to take, and you need to know all the resources. Okay? Sometimes with the databases, you need to lock a record in a database. Okay? And there are thousands of locks in a database. And you may not know which ones you are going to use. And it may not be easily possible to satisfy this ordering need. So we need to come up with a solution. This is the solution. Okay, let's make some definitions. There are 5. By the way, I made another mistake here and nobody is telling me, right? This is not... Is that correct? When I do that, it is... I think I should start with process number... philosopher number 0, right? It is philosopher number 0 and resource number 0, because otherwise this wouldn't work, right? When it comes to 5, yeah, 5 plus 1 is already, yeah, that's not true. So philosophers should start from, it should start from 0 to 4. And resources are, again, forks are from 0 to 4, so that this modulo can work. Okay, so there are 5 philosophers, okay, and each philosopher could be either thinking, hungry, or eating. So thinking means that I am in this function. I am thinking, and eating means that I am in this function. I am eating. I take all the resources. Hungry is that I am in this process. I am trying to get the forks. Okay, so I can be, as a philosopher, as a process, I can be in 3 states: think, take fork, and eat. Okay, that's what it says. Theory defines. And there is one more simple define left and right. If my philosopher number is I, my left is, let's get the n, right. My right is I plus 1. If I am the philosopher number 0, okay, my right would be 0 plus 1 modulo 5, it is 1. My left would be 0 plus 5 minus 1 is 4, modulo n is 4 again, okay. So if I am the philosopher number 0, my right is 1, my left is 4, okay. So it just uses this I, and it makes this simple. It makes this simple. It makes a simple calculation, modular based calculation. And then what do we have here? We have semaphores. Okay, as you know, semaphore is a simple integer. Okay, we have a type def in semaphore. We have a mutex semaphore. Okay, initial value is 1, and we have 5 semaphores. So it looks like each philosopher is going to have a semaphore, and there is going to be one global mutex to mark the critical region. To mark the critical region. Okay. Good. Okay. Let me try to make this right by doing this. How about this one? Let's say I have a mutex. Mutex m initial value is 1. Okay. And here I write down m. Okay. And here up m. Would this solve the problem? So I made all the non-thinking parts, taking fork, left fork, right fork, eating and putting the forks back in a critical region, mutually exclusive region. Would this solve the problem? Do you see any? Do you see any? Do you see any race conditions?
Sir, I didn't get what you did here with down and ups. Can you rephrase it again?
Do you don't know how the mutexes work?
No. Why did we do down and ups here? What is the reason in this context?
This is my critical region. If this is my
Correct.
critical region, if I am in the critical region, while I am taking the forks, nobody can be in the critical region. So there cannot be any switch here, right? That was the problem, right?
Mm-hmm.
So I prevented it. Did I solve the problem? That's the question.
No, process may take the mutex that try to take the fork, but it could be lock and
It
mutex.
cannot be locked. Nobody can take the fork without taking the mutex.
Yes, this will not cause a race condition, but this will only limit us to one process working at a time.
Did everybody hear that? Osama, say it again.
This will not lead to a race condition, but this will limit us to one process going at a time.
Did everybody understand that? He says that, yeah, there is no race condition now. If somebody takes a fork, that means that he got the mutex. Nobody could be in this region. Okay? Only I can be in the region, or I am blocked at here. So that means that this means what? Only one person can eat at the same time. Only one person can eat at the same time, right? And If this is what you want, then there is no race condition. Well, in that case, that means that there is no parallelism, right? Even though I have two processors, even though I have resources available and everything is available, I am letting only one process run. So that would be the kind of solution. So if you don't have any parallelism, if you don't have any multi-programming, then you don't have a race condition. Yes, that's true. But we don't want that, right? We don't want that. Okay, good. How about this one? How about this one? Instead of here, I am saying up and so my critical region is only the taking the resources. What is the problem with this solution? So I am taking these two forks as a unit. Take fork number 1 and take fork number 2, both of them. Okay. And there cannot be any switch while I am doing this. What is the problem with the solution?
Another philosopher may starve.
Another what?
Another philosopher cannot take fork because it's taken by another philosopher. So he or she may starve because
Why do you say so? Because after I take the forks, okay, after I take the forks, so what happens after?
philosopher will eat, but didn't
After I take the forks, I
didn't
release the mutex and I start eating. When the second one comes in, so what happens?
Sir, maybe context switch happen between eat and put fork I. So we switch without put fork. So no one can use fork I and I plus 1.
No, I hold the mutex. Okay, I hold the mutex. I take fork number 1 and context switch happened. The second process cannot enter the critical region because I am holding the mutex.
But maybe it happens after between eat and put fork.
Eat and put fork, a
Yes.
context switch happened.
Yes, so we can't use fork I and I plus 1 because we didn't put them.
Yeah, so I am going to be blocked in here. Is that what you are saying? I am going to be blocked
Yes. Yes, sir.
at that point because I cannot get it. I am blocked and I am holding the mutex. Nobody can enter. So that's going to cause another deadlock. So the only way this will work is I will take this here, and you know the problem with this one. Okay, let's go back. So trivial solutions will not work other than this ordering. And if I do the ordering is like this: 0, 0, 1. Okay, all the resources, and the process number 1 should take fork 0 first and fork 4 next. Then this will work. But again, as I said, this is the general solution. So okay, let's look at this one. So the philosopher number I says that, okay, I am going to think and I am going to take forks and I am going to eat and put forks. So there is no mutexes, or there are no semaphores in this code. So that means that take forks and put forks must be having this solution here. Okay, let's look at these take forks and put forks. Okay, let's look at them. As I said before, don't think that these are philosophers or the forks. We are just trying to make things more interesting by making these kind of analogies. Okay, so take forks. Okay, so this is down mutex. I lock my mutex. Remember, my globals. There is a mutex initial value is 1, and there are n semaphores. They can be incremented, decremented, etc. Okay, and all the semaphores, their initial values must be 0. Okay, their initial values must be 0 at the beginning because I did not initialize them. Okay, good. Okay, so this is take forks function. Remember, I take forks, I eat, and I put forks. Take fork says that, okay, I'm in a critical region. This part is in a critical region. My state I, okay, my state I is hungry. State I means it is here. Where is my state? It is here, okay. So there is an array of states. There is one state for each philosopher, and states could be thinking, hungry, or eating, okay. And there is a mutex global, and there is a semaphore array. Okay, so my state is hungry, and I call this function test I. This test I is going to take the 2 forks that I need. Okay, if I am the process number 0, I will get resource number 0 and 1. Test is going to take those. Once I get the resources, I will up the mutex, so I am out of the critical region. But then there is something funny going on here. It says that down Si. Remember the semaphores? It is trying to down the semaphore of my semaphore array. So the semaphore values at the beginning are all 0. So this is going to block myself. So that means that this test I is doing something with the semaphores. Let's look at this test I. Where is test I? Where is test? Test I is here. So the whole trick is in the test I actually. Test I says that if my state is hungry, and if my the philosopher on my left is not eating, and if the philosopher on my right is not eating, I am hungry, on my left and right is not eating, that means that all the resources are available, then I can start eating. Okay, so I was in the hunger state, I can start eating, and this is the trick here. I am incrementing the semaphore by 1, my semaphore by 1. Okay, remember left and right are macros. Okay, they are used for calculating the left and right positions. Okay, so if I am hungry, if my left is eating, if my right is eating, not eating, that means that I can do that. I can do that. So if this is not successful, if my state cannot be eating, what happens if I don't enter this if statement? If I don't enter this if statement, let's go here. If I don't enter that if statement, my state will stay as hungry. I will be out of my critical region, and I will try to down my semaphore, but my semaphore is 0, so I will be blocked here because I didn't get the forks. Okay, so I couldn't get the forks. But if I did that, if I am hungry, if my left is not eating, right is not eating, then I am eating, and I opt my semaphore. And when I come here, since my semaphore is 1, I can down it, and I can leave this function, and I can take these forks, and I can continue eating. So how does this take fork? What is the condition for these take forks function to block? tell me the condition that causes this take forks function to block.
One of the adjacent processes or philosophers is reading.
Yeah, either left or right. Okay, this is the condition. Either left eating or right eating, or both of them are eating, or I am not hungry. In that case it would block. I am not hungry. In that case it would block. But you might say that there is no way that you cannot be hungry because state I is hungry. Okay, so in this case, for the take forks case, it will only block if my left is eating or right is eating or both of them are eating. If both of them are not eating, if none of them are eating, then this function will not block and I will start eating. But the interesting is that blocking happens here. Blocking happens here. I am waiting for the semaphore to be non-zero. So that means that one of my neighbors, whenever they are done with eating, they should up my semaphore. Okay, they should up my semaphore, and we are going to see it in a few minutes when we look at the put forks function. Okay, so that's the story about take forks. Let's look at the put forks function. Put forks is here. Okay, put forks says that, okay, this is my critical region. Okay, since I am done eating, I will start thinking. Now my state is thinking. Since my state is thinking, okay, I am going to check my left and right neighbors. If they are waiting for the forks, they can have it. So I am testing left and right. I am going to call this function again. Okay, so let's say if my I is 2, okay, state I thinking, yeah, I did that. I am going to test left, so that means that I am calling test 1 and I am going to call test 3, right? So test 1 says that if state I is hungry, okay, if state I is hungry, if state 1 is hungry, if my left, that is 1, is hungry, it may not be hungry. So if it is hungry, that means that he cannot be eating because I had the forks. So it means that it wants the forks. So but the only way that it can have the forks is if state I is hungry and left of my left is not eating and right of my left, which is myself, is not eating. I know this one. Okay, then my left can start eating. I am going to up its semaphore. Remember, my left, if I am doing this, remember my left must be waiting on the semaphore. And I am doing the same thing for the right. Of course, if I am calling this on left, I know that I am not eating. This is going to definitely be false, and this is definitely going to be true, and for the right, this is going to be definitely true. But to be compact, they are just using the same test function. Okay, so the trick is, before you start eating, you check your neighbors. If they are not eating, okay, if they are not eating, I can take the forks. But if one of them is taking, then I will put myself on a hold on a block because there is a down here. So if you look at this, take forks, okay, can block either here or there. Okay, put forks can block only here, and that's it. There is no blocking for the put forks function. Okay, so that's the dining philosopher's problem. This is general enough, and this will work for multiprocessor systems too. And you don't need to know, okay, you don't need to know the ordering of the resources, or you don't need to know how many resources you need at the beginning of the function, etc. So this is a general enough technique to solve the race condition with these kind of cases. Well, I mean, I think I told you that uh, writing parallel programs, multi-processing programs, multi-programming programs, and doing the inter-process communication right is not a trivial thing. There could be some problems. There could be some problems which you may not notice in the first look, and those problems may surface very late in your deployment of the programs. And that's the life for a parallel programmer, actually. That's why, remember the monitors? That's why they invented the monitors, to make the life of a multi-programmer easier, but that doesn't solve everything. You need to be careful. Okay, any question about this dining philosophers problem?
Sir, may I ask a question?
Sure.
We have only one global variable mutexes, right?
No, we have many. We have global variables, we have the mutex, we have the state, and we have the semaphores. Two arrays and one mutex.
Yeah. I mean the semaphore mutex.
There is one mutex, yeah. There is one global critical region mutex.
So it seems that it can block the other philosophers or processes
Sure,
to get
yeah.
work,
Uh-huh.
even if they are not neighbors with each other.
Yeah, that's true. But I need to do that because I am talking about modifying the state global variable. And state global variable is shared between the philosophers, and they read and modify it. While I am reading and modifying it, see, this one says that if I am hungry, this one says that I am hungry, then it's called the test, and test modifies the state again. So reading something and modifying it is going to be done at the same time, so I need to lock the global mutex. Otherwise, there would be very terrible race conditions.
Okay, sir, thank you.
Any other questions? Okay, if there are no questions, then there is another classical example, readers and writers problem. Well, you are lucky. You are lucky. I am not going to give you the bad code for this one. Okay, readers and writers problem is this. Okay, you have a database. Okay, there are many reader processes. Okay, there are many reader processes that will read this database. Okay, so these are the readers, and there are similarly there are writers, writer process 1, writer process 2, and writer process 3. Okay, they are all sharing the same database. Question: how many readers can read the database at the same time without causing any problems, any race conditions?
No limit.
All of them?
There is no limit, right? I mean, reading is free. I mean, you just read it. You are not modifying it. Reading doesn't cause any race problems. Writers do, though. Okay? So how many writers can write to the database at the same time without causing any problems?
One.
Just one.
Number of data.
Yeah, just one. That's it. So that means that I should have some kind of a system that will let as many readers as you like, okay, in a database. But if a writer is using the database, then no other writer or no other reader is allowed to take the database lock. Okay, so all three can be reading the database, but if one writer is using the database, nobody else can write to it or nobody else can read from it. Similarly, if a reader is reading a database, okay, no writer can write to it. Okay, we are going to do this. Okay, in an infinite loop, this is what the reader does. Okay, maybe we should look at the writer first, then the reader next. These are my globals. Okay, I have a mutex. Okay, and this is for critical region mutex, and I have a database semaphore. Okay, so that means that this number can increase from 1 to 3, 4, 5, whatever, and there is a reader count. So this reader count is going to tell us how many readers are reading the database at that time. I don't have a writer count because writer count could be either 0 or 1. You cannot have it 2. Okay, if reader count is different from 0, the writer count cannot be 1. Okay, so let's look at the code for the writer, which is a little bit more, okay, which is a little bit more a little bit easier to understand. Okay, in an infinite loop, it thinks up data. Okay, it tries to get the database's access down database, writes the data and ups the database. So DB is a, remember, DB is a semaphore. Initial value is 1. So both of them are actually controlling access to something. So down database, if it is 1, it's going to write it. If it is not 1, if it is 0, it will be blocked. So it's a very regular blocking and unlocking stuff. Down database, right, and up. If database is available, I am going to do that. Okay, so this is going to satisfy all the things. Only one writer can do it, right? Only one writer can write to it. And if since this is the writers are calling this function, if a reader is reading the database, he must have done the DB. Okay, so let's look at this reader part, which is more interesting part. So first I enter my critical region mutex. Okay, to be able to get the critical region, I down this mutex. I increment the reader count by 1. And okay, this is the tricky part. If reader count is 1, down DB, what does that mean? As a reader, I down the database lock only if I am the reader number 1. That's what it means, right? As a reader, I down the database DB lock if I am the first reader to go in. If the lock is not available, I will be blocked. Okay, I will be blocked in this critical region. So nobody can enter the critical region, but this critical region for readers only. So what is the only condition for a database to be locked? One writer must be writing to it, right? So if a writer is writing to it, I am blocked in here. All the other readers are going to be blocked there because I am holding the mutex. So I will wait. I will wait until when? I will wait until the writer writes to it and releases the database lock. Okay, so that's what happens. So the thing is that I don't down this lock for all the readers. Only the first reader to enter the database is going to down this database. Then I up my mutex if I am not blocked. I up my mutex. I read the database the way I want, and then when I am leaving the database, I down the mutex again. I decrement the reader count by 1, if I am the last person, if I am the last reader to read the database, then I up my DB. Okay, the first reader downs DB. Okay, and all the others, they just increment this RC. So there could be 100 readers reading it. They have the DB lock. But the last reader that leaves this area ups this DB so that if a writer waiting on it, the writer can get N. And then I up my mutex. So this is my critical region. Another critical region is, sorry. So this is my critical region. Another critical region is here. Okay. So that's it. That's the whole readers and writers example. Of course, this is a generalizable. This is a generalizable code. This resource doesn't have to be the database. It could be just a global variable. That's it. I mean, if many processes are reading a global variable, and some of them are writing to it, then you could use this model, readers and writers model. Okay, we already did the producer consumer example. Okay, we had a solution for that one too. Okay, these kind of solutions are a kind of standard. So the lucky thing is that, as I said, writing multi-programs is not that easy, but luckily you will have these kind of pattern programs. Okay, you follow them and you find a model that is similar to your problem and you modify it, and at the end you will end up not having any race conditions. Okay, any questions on this? Any questions? This doesn't allow any race conditions. Yes, that's true. But there is a bad thing about this readers writers solution. Can you tell me what this is? There is a bad feature of this, downside of this solution, readers writers solution.
Writers may not be take the mutex.
Yeah.
Mutex.
They can starve, right? If there is a single reader, if this is a busy system, okay, let's say I have a reader, a writer, writer, reader. Okay, so a reader is reading the database, yes, another one, and writer has to wait. While writer is waiting, this one can read, this one waits, this one can read. So it may take for a busy system, for a writer, until infinite amount of time to get the lock of the DB. So the writers might starve. That's one bad thing. Well, you can come up with solutions such as, if you may not, for example, allow any readers to go in while there is a writer waiting and etc. You can do those prioritizations. Okay, so that's it. I am going to take 8 minutes of break. After you come back, the system will automatically give you my next quiz. The quiz will start at 12:30 and it will end in 10 minutes. And after that, we will continue with the next chapter. Okay.
Okay.
See you in 18 minutes. Okay, time is up now, 12:41. Let's start our lecture then. Okay, I don't think that I will give you the answers because this lecture we talked about that code. If you want the answer, just watch the lecture video again. And for the second question, a semaphore, a mutex is a very specialized semaphore. The implementation is exactly the same. For the down part of the mutex is same as the down semaphore. Up part is the up semaphore. That's it. Okay, so I will try to do this from time to time, and I am not planning to give you the exact time of the quiz. So the quizzes will be more like pub quizzes. I may start the day with a pub quiz at the beginning of the lecture. So please be on time. Okay, so let's start this memory management, chapter number 3. We have been talking about multi-programming, and the idea of multi-programming gave us this concept of processes. Each process would think that they have the complete CPU, and they can do whatever they want with the CPU as long as, of course, they are using their allowed instructions and etc. And they don't think about the other processes unless, again, you need to do the inter-process communication. So that was a very nice abstraction from the operating system, but it was difficult, right? Managing all those processes, who is going to run next, and keeping all the process related data in the process table, and trying to minimize the context switching and etc. It is a lot of task for the operating system. We like to do the same abstraction. With the memory management. We like our processes to think that they have the whole memory. Okay, they can do whatever they want, but of course this is not going to be a real memory like the processes. The processes, they think that they have the CPU, but in fact they are using kind of a virtual CPU. Okay, so everything they do is controlled by the operating system. How? If they do something wrong, CPU causes a trap to the operating system, and operating system takes over. If they use too much CPU, some interrupt is produced, and that interrupt is handled by the operating system, etc. So we get lots of help from the hardware, from the CPU, and the processes uses the CPU this way. And if there is something that the operating system needs to run, the hardware helps us in starting the operating system. Again, we are going to do the same thing with the memory. The main idea is each process will think that they have their own address space, and they are free to do anything with that address space, and they will not think about the other processes address spaces at all. Lamia, do you have a question? Lamia Ceren, do you have a question?
No, no, teacher. No, professor.
Okay, you have your hand raised. Okay, so memory is something precious. Okay, we like to use our memory as careful as possible, because doesn't matter how much memory you have, your programs will use it to the end. Memory is never enough. Okay, in 1960 they said that whatever memory you have, doesn't matter if it is 1 kilobyte, 5 kilobytes, or 128 kilobytes, or 5 terabytes, your programs expand to fill the memory available to hold them. Okay, so this is IBM 7090 from 1960. I think this is one of the IBM mainframe computers that don't use the vacuum tubes, this computer uses the transistors, so one of the early ones, and the total memory of this computer was, okay, 32 kilowords, and I think each word is 16 bytes or something, so it has a 16 bits or something, so it has a total of 64 kilobytes of main memory. And in today's money, this computer costs $20 million. Okay, in today's money, it costs around $20 million. Nowadays, any computer that you can buy, the cheapest one cheapest one that you can buy for less than $1,000 or maybe $500 will have hundreds of thousands times more memory. Still, we have to be careful about the memory. That doesn't mean that we have lots of memory compared to 1960s. In fact, whatever the memory management techniques they invented 1960s, we are using those techniques to manage the memory. Okay, our memory is resource, and remember, one of the tasks of the operating system is the resource management. One of them is hardware abstraction, abstract the hardware, so that the programmers users can use the complicated hardware. Okay, the other one is manage the resources such as the CPUs and the memories and the I/O devices, etc. Okay, if we didn't have multi-programming, okay, if we didn't have multi-programming, things would have been much simpler. This would be the solution. Okay, this is whole your computer system. Address number 0 starts here, and there is a large number. Let's say I have a total of 64 kilobytes of RAM in my system. At the bottom part of the memory, I have my operating system, all the device drivers and etc. And I have my simple user program, and that's it. This simple program knows that it can start from this address up to the top of the memory. It can do whatever they want. Okay, or sometimes they do it this way. Okay, they put the operating system in ROM, read-only memory. Okay, so you cannot erase it accidentally or on purpose. So operating system is fixed, you don't modify it, and user program is there. Sometimes they did this. Okay, they say that, okay, some parts of the operating system is in the ROM, it cannot be changed, but most of it is in the RAM in the bottom part of the system. Of course, if there is no protection, usually we don't have a protection, memory protection in these kind of simple systems. A user program can accidentally wipe out the operating system in this case or in this case. I cannot write on these positions. I can only read them, but sometimes I can wipe them out. Okay, good. So, but we don't have this case. Okay, nobody's using these kind of computers anymore. Even the simplest ones run this nice operating system of Linux. Okay, and Linux allows multiple programs using the same system. And if you have the multiple programs, then then of course the idea of process is there. If the idea of this process is there, each process should think that they have their address space, and we should be able to handle these kind of cases. Let's look at this simple case again. Let's say I have two programs. Forget about the operating system. Okay, let's say we are doing the things without the operating system. Hypothetical situation. First program. Okay, I have total of 16 kilobytes of memory available, and this computer, as soon as it starts, okay, as soon as it starts, this program says that jump to address number 24, and address 24 says that I like to do a move instruction, some register instruction, then some addition, etc. This is a regular program. Another regular program is this. As soon as this program starts, it jumps to address number 28, and the first thing it does is comparing something with something, etc. So nothing interesting so far. Let's say I like to do multi-programming. I like to keep these programs in my memory, and I like to switch between them from time to time, either preemptively or some other way, the ways that we know. Okay, and we'll ignore the operating system part. So I need to load these two programs in my memory at the same time, and which is I did. Okay, so this time let's say I have 32 kilobytes of RAM. Okay, so I put my first program 16 kilobytes in the first part and other 16 kilobytes in the second part of the upper part of the memory. Okay, so when this program starts, this program A and this is program B. When this program starts, we know it wants to go to address number 24 and do this move instruction. Okay, it does that and it does addition, etc. But when this program starts, it says that jump to address 28, because this one assumes that it has the memory by itself. But address 28 is here. It is not this one. It is not red anymore, because this process doesn't know that it is going to live at some other part of the memory. So we need to find a solution for this one. Otherwise, there is no concept of address space. Otherwise, if this program knows where it lives in the memory, if this program knows that it lives at 16th kilobyte of the memory, that means that it knows where it is. So and it knows that it shouldn't access anywhere else in the memory. And if by accident it modifies some things in the first part of the memory, that's going to be bad. Or by purpose, if it does that, that's going to be even worse. And that's not nice. That makes writing programs a lot difficult. You have to think about the other programs. It's like writing multi-programs, but you have to think about the other programs. It is difficult. So in the processes, we don't think it that way. We write our processes and we let it run. And I like to do the same thing with the memory. So we are going to get help from the hardware, and hardware is going to be controlled by the operating system. And we will be in a case that each program will think that they are running in such a nice machine and they are running in such a nice machine. In fact, they are using different parts of the memory and their addresses are different. Okay, one solution that the book suggests is static relocation. Okay, I am not going to let the program know that it is using a different part of the memory, but I will do this. I will say that this program, say that jump 24. This 24 is not an absolute value, or this 28 is not an absolute value. If I move this part of this program to this part, maybe I should add this number 16,384 to all these kind of jump statements, or the load statements, or the store statements, or the function call statements, etc. So this is called static relocation. At program load time, when the program is loaded to the memory, okay, the execution address is known. So what I do is I modify each instruction one by one. If it contains a absolute address in the memory, I modify it so that it reflects the new location of the program. Okay, so that's one solution. When you are loading the program, we can do this kind of modification in our program. So that means that loading our programs will be difficult, right? Why? Because our compilers or our programmers has to mark some of the instructions to be modified. Okay, we need to say that, okay, you need to modify this instruction when you are relocating my code and etc. And if by accident from this program B, if by accident, if I modify anything in this part of the memory, it will be allowed, and that's a bad thing. So there is no protection. So this static relocation it solves some of the problems, but it is not as nice as having your own address space. Okay, and you need help from the compilers and the hardware architecture. So nobody uses this kind of a solution. And the other thing is this: we like our programs to think that they have a very large memory, even though okay, this one thinks that it has 5 gigabytes of memory. This one thinks that it has 5 gigabytes of memory. Another one thinks that it has 5 gigabytes of memory, but in total I don't have 15 gigabytes of physical memory. I have only 8. Okay, so I like my processors think that they have 5 gigabytes of memory, even though the total of them will not fit into my memory. So the static relocation cannot achieve that one. Okay, cannot achieve that one, and I like to achieve that one too. So they have invented these address spaces. Okay, and this sentence is important here. The idea is, I think I repeated this many times. Just like the concept of processes, okay, the concept of processes abstract the CPU. Okay, the address space, the concept of address space creates a kind of abstract memory for programs to live in. That's the invention. So process, the idea of process and threads, they abstract the CPU. Okay, address space, idea of address space abstracts the memory. Our programs usually, they don't know what is going on with the memory actually, because they are living their own address spaces. They are living their own address spaces. Like our processes don't know that they are being interrupted all the time. Okay, CPU doesn't run our programs continuously. CPU does many other things by interrupting our programs. Okay, doing many other things, but our programs think that they are the only owner of the CPU, and we like our programs to think that way about the memory too. Okay, they think that they have a very large memory, contiguous memory. They are using it, and in fact, okay, they are sharing that memory with many other processes, and their address space is not contiguous. It is all distributed. Okay, and some of their data may not be in the main memory at all. They don't know. Okay, so the address space is the set of addresses that a process can use to address the memory, starting from address number 0 to some high number. Okay, so protection has to be addressed. Since each program has its own address space, okay, their own address space, they cannot reach the other process address spaces. So this has to be satisfied with the hardware and operating system. And the relocation. Our programs should not know where they are actually in the main memory, or should not be sensitive to that information. Okay, so relocation and protection has to be solved. Somebody came up with this idea. They say that let's have 2 registers, and this is similar to static relocation, but we call this dynamic relocation. Why? It will be clear in a few minutes. They say that we are going to do the dynamic relocation. What does that mean? It means this: I have 2 registers, like stack pointer, program counter, register A, register B, etc. I have 2 registers. One is a base register, the other one is the limit register. Whenever I try to reach the memory, I always add my memory address with this base register, and I make sure that the resulting address is not larger than limit register. Okay, maybe this picture will make it clearer. Remember my process that I have loaded at this address of 16 kilobytes. So I have loaded my process B at this address 16,384. Okay, at that address. And I have two registers. One is 16 is base register, which contains this number. Okay, and the limit register is the length of the memory that I have. Okay, when this instruction says that jump 28, okay, I automatically add this number with this number and I reach this position. So this is called base and limit register solution. Instead of doing the static relocation when by the operating system when I am loading the program to the memory, I get the help from the hardware. Of course, these are from the hardware, and these two registers are used to find the physical memory address for our programs. Our programs still think that this program thinks that it is jumping to address number 28, and in fact it is jumping to this address because all these kind of numbers are added. All these numbers are added to the these kind of absolute addresses. Okay, so this looks like a nice solution, but as always with these kind of simple solutions there are problems. What is the problem? Problem is this: you have to add these numbers with these numbers all the time whenever you need to access the memory, and addition is expensive. Okay, every memory reference is an addition and comparison. What is the comparison? I add this number with this number, okay, and the resulting number is larger than the limit, then I will say you are out of limits. Okay, you cannot do that. That's the protection part, but I need to add it. Okay, so every memory ref is an addition and comparison. Comparison can be done very fast way in parallel. Okay, comparison can be done in parallel, but addition has to be serial. Remember, you did the full adder in your hardware courses, right? How does the full adder run? You take one bit, another bit, you add them, you put the result here, but there is a carry, right? And you put the results and there is a carry. So there is a carry bit, and carry bit has to be propagated serially to the other bit additions. Okay, bit additions. Also, I didn't solve that problem of my programs, 100 programs not fitting in my main memory. Okay, remember on this computer, on my computer, once we counted it, right, there are more than 100 processes running, and if each one needs 1 gigabyte of memory space, that's going to make total of 100 gigabytes. I don't have that kind of memory, and only a few people in this world have that kind of memory in their laptops. Okay, so what is the solution? Solution is don't keep all the parts of your programs in the memory, okay, because I don't use them all the time, so you keep only a small part of it. This solution doesn't do that. Okay, this solution loads everything in the memory, and whenever you switch, of course you need to save your base and limit registers in the process table, and whenever you switch you need to update your base and limit registers. Okay, good. So we didn't like this either, so what are we gonna like? We are going to like this swapping and virtual memory. That's going to be the main topic of this whole chapter: virtual memory and swapping. Swapping means that we don't have to keep all of our programs memories data on the main memory, on the RAM. Okay, let's keep some of them on disk. So whenever we need, we swap that data between the disk and the main memory. That's the idea of swapping. Virtual memory is each process would think that they have their own address space from 0 to some large number. Okay, so our processes will use some kind of a addressing mechanism, but in reality, in the physical world, okay, that addressing mechanism will be different. Okay, so that's what we are going to do. So the swapping is this. There are many versions of swapping. One of the most primitive ways of swapping is this. Okay, if the physical memory is not large enough to hold all the processes, if I switch from one process to another process, then I would write my blocked program to the disk. I would swap it to the disk, and I would load my running program from the disk to the main memory. This is called swapping. Okay, but this is, as you see, this is very inefficient. Remember, context switching is inefficient, right? If we do it this way, it becomes even more inefficient. Why? Because as soon as we do the context switch, we have to write the whole process to the disk. We have to read the whole process from the disk. That's not efficient. But bear with me for a few moments, and let's see the swapping this way. Let's see the advantages of it and disadvantages of it. As it is, as I have mentioned it, this is expensive. Okay, writing the program to the disk and reading it whenever it is loaded. Let's say I have a case like this, and there's an operating system. I have my program A, and I loaded another program B, and I loaded another program C. Let's say these are using base and limit registers. Okay, base and limit registers, and that's fine. Okay, and then I need to load another program D. Okay, at this point I need to load another program D. Okay, but D doesn't fit in this empty space. What am I gonna do? I need to write one of these processes to the disk and make some space available. So I had chosen A. A is going to go. A will be written to the disk. Now I have good enough space, large enough space to fit my D in here. Okay, now three programs are in the main memory. They are running, but then I needed to switch back to A again. So what am I gonna do? I cannot fit A in this position. It is not large enough. I cannot fit A in this position. So what am I gonna? Maybe A is large. A is small enough to fit into the sum of these two areas. Maybe, but they are not in contiguous configuration. Okay, they are at different parts of the system. So what do? I swap B out now, and I loaded A back in. So it might work, but it's going to be very inefficient. It's going to be very inefficient because switching between programs is going to take lots of disk input output, and that's expensive. That's expensive. Okay, good. So, but the idea of swapping, although will not be used like as simple as this, will be there. We are going to use swapping because we cannot fit all the data of the programs in our memory. So we have to swap in and out some data, but we are not going to do it this way. Okay, we are not going to do it this way. Okay, any questions so far? Any questions? No? Okay, then I will go on. So when we say let's load a process in the memory, when we say when let's load a process in the memory, what does that mean? Just you load the code itself, runnable code. How about the heap? How about the stack? But at the beginning of the program, our heap and stack is empty. And I know that they are going to grow. So what is the idea? Idea is, okay, probably allocate more space for the process than needed at the beginning. Okay, needed at the beginning. So you are going to allocate more space than needed, and when the program expands during the execution, we will end up using those parts of the memory. Okay, so that's the idea of allocating more space. Of course, when we swap out our programs, we don't write anything to the disk from the unused memory parts, because we allocated a little bit more. Of course, and when we are writing programs, swapping, let's say I am swapping this A to the disk, right? I don't swap the parts of the memory that corresponds to the code. Why? Because code doesn't change, right? Code doesn't change. Your heap changes, your stack changes, okay? Your variables change, but your code doesn't change. So when you are swapping out programs, you only swap out your modified data. Your code, it doesn't get modified. So swapping might include some smart decisions like these. Okay, and here's an example: operating system, and let's look at our Unix cases first. Okay, operating system, program A and program B. Program A, there is the code part, there is the heap data, and there is the stack. And for the B, it's like that. And this part here, at the beginning, it is not used. It's kind of inefficient, right? I need to have this empty space in my programs, okay, for the room for growth. Still, my main memory is not enough to hold other processes. So I am wasting these empty spaces. But on the other hand, I have many processes waiting on the desk to be loaded to my main memory. So we need to find solutions for these. Okay, we need to find solutions for these kind of problems. That's called swapping. Okay, good. Um, what did we say? We said that memory is a resource and it has to be managed. So the operating system should keep track of who is using what part of the memory, or what parts of the memory is available. How do I allocate them? Okay, so this is done dynamically, of course, while the programs are being loaded. Okay, the operating system is doing this management, and operating systems usually keep these free parts of the memory, or the allocated parts of the memory, using two approaches. One of the bitmap approach, the other one is the free list approach. Here is an example. Okay, let's say I have 1, 2, 3, 4, 5, at least 5 programs in my main memory. Process A takes this part, and let's say these are my memory blocks. Let's say these are 4 kilobytes. Okay, so the process A takes 4 times 5 kilobytes of data space in my main memory. So process A, the size of the process A is 20 kilobytes. This part of the main memory is empty, nobody is using it. This part is process B, and process B is using 6 pages or 6 blocks. Okay, let's call each of them blocks, memory blocks. Okay, these are memory blocks. Okay, the size of the memory block is a system decision, and there is of course a trade-off for large blocks and small blocks. Okay, the first approach to keep who is using where and which parts of the memory is empty and occupied is using a bitmap table like this. So let's say I have a total of, let's say I have a total of 2 to the 20 bytes of memory space. 2 to the 20 is 1 megabyte, right? It is 1 megabyte of memory space. Okay, and my block size is, memory block size is 2 to the 12, right? So it is 4 kilobytes. 4 kilobytes is 2 to the 12. So how many blocks do I have in my main memory? How many blocks do I have in my main memory?
2 to the 8.
2 to the 8, yes. That's because if I divide this with this one, if I divide it, I would get 2 to the 8. Okay, so I have 256 blocks. So what is the size of this bitmap table then? It should keep 256 bits. Okay, so these 5 bits show that the first 5 blocks of the memory is occupied. Then the next 3 blocks are not occupied. Then the next, I don't know, 5 plus 6 plus 4, 12. Next 12 blocks are occupied, and etc. So I know that operating system can see this part of the memory is available, this part of the memory is available, this part of the memory is available. If a new process needs 12 kilobytes of memory space to be loaded, then operating system can say that, okay, I know there is a place here by looking at this table. Okay, that's the first approach. The second approach is a linked list approach. That's the same thing. So for the same configuration, I keep a linked list of occupied and not occupied, occupied and not occupied nodes. This one says that the blocks starting from 0 for 5 blocks, it is occupied. Okay, but the block starting from block number 5 with 3 blocks, it's a whole, it is not occupied. Then from 8 to 6, okay, 8 plus 6 is occupied. From 14 to 14 plus 4 is occupied, and there is a whole, it starts at 18 and it continues for 2 blocks, etc. So this is the linked list approach, this is the bitmap approach. Okay, if I have only a few processes in my memory all the time, which one would you prefer in terms of memory usage?
The bitmap.
If you have only a few processes, you like bitmap better?
Yes.
What kind of system is it?
As simple as possible. I mean, this is the whole thing, this is the whole picture. If I have only one process in my memory, so you would prefer the bitmap. Why?
Because it takes very specific amount of space.
So you are going to waste your 256 bits. Doesn't matter how many processes you have.
The question is if I have a small memory or small amount of processes.
If you have only a few processes in your memory.
Oh, then the other way around. I thought you asked about if I have a small amount of memory.
Okay, if you have only a few processes in your memory, this linked list approach is better. Why? Because you will have only 2 or 3 nodes. But this one is always fixed. Doesn't matter if you have 100 processes or just one process. You need to keep that table. You need to keep that table. Okay. And one problem for the operating system is finding the empty spaces in this memory management data structures. So I have a new process. I need a new area to load my process. So how should I find it? You will make a linked list search or a bitmap search. Okay. Question for you. If I have a new process that needs 2 blocks of space, which positions would you use? This one or this one or that one? It needs 2 blocks, just 2 blocks.
The one in the middle.
Why?
Because if a process later asks for 3 bits upload, I can give it another.
So you are thinking about the future. So you are saying that, how about one? If you need 1 block of memory space, which one would you use? This place, or that place?
In the middle one.
Why?
Because it's small compared to others, but also when process needs more space, there is also more space for that.
Well, it can fit in here too.
Maybe it's about...
Yes, but it occupies more space than way more space than it needs.
Isn't that a good thing? Because if I allocate this space, okay, like that one, I have 2 more blocks in here. So a new process comes in, it wants 2 blocks, I can give this one. But if I allocate it here, right, only 1 block is available, and you will rarely get such a process. Only 1 block. So this place will be wasted. So which one is better? The answer is no, we don't know. We don't know. The answer is, it's a difficult question. One is trying to find the best fit. The other one is trying to find the worst fit. Okay, leave as much as possible, etc. And we are going to see it in next week. Today I am out of time now. Are there any questions about the current?
Yes, sir.
Yes.
I'm asking free space. I mean the extension part of the program. How does the operating system decide how much expansion will a program will need?
Okay. You usually look at your history, and you may ask this information from the programmer. The programmer might say that I am going to need at least this much of memory, and at most this much of memory. You could do that, but there is a very nice solution. None of these problems will be relevant. Okay, our solution of virtual memory. Okay, our programs will think that their address space will start from this 000, and there at the top they have this very large number. Okay, our programs will think that all the data, all the address space is available between this 0 and very large number is available in the memory, but in fact most of the space will stay on the disk. It will not be loaded. It will not occupy any space in the main memory. Okay, that problem is automatically solved most of the time.
Okay, thank you.
With the idea of paging and virtual memories, and that will be clear. That will be clear next week, beginning of the first lecture next week. Next week on Monday, let's talk about what date we are going to do our midterm exam, because we are supposed to do it next week. but it looks like we didn't make a decision. Okay, so on Monday, just remind me that we should make a decision on the midterm date. Okay, that's it. See you
Sir,
on.
is it for sure that it's going to be a paper exam?
No, it's not going to be a paper exam. It's going to be an online exam again.
No, I mean not project.
No, it's not going to be a project. It's going to be a online classical open-ended questions. You will need your camera. Okay, we'll ask you questions and you'll answer them. By the way, from yesterday's quiz, I graded your quizzes. 10% of the people, they think that it is okay to go to Google and type my questions and copy and paste it. I don't know where you get that idea. So 10% of them don't see anything wrong about it because they are doing it in a very apparent way. I mean, they just paste it from Wikipedia, even though I warned you. I don't know what is wrong, but that's not the idea. I mean, I am giving you an exam. You are supposed to answer it. I know how to type my questions on Google. Okay? I am trying to understand if you are listening to my classes. I am trying to understand if you got what I am trying to teach you. So it is not okay to get the answer from Google and type it to me. Some people just directly copy paste it. It's like 10%. And 5% they went to the web again. They read the answers and they tried to understand it and give me an answer from that. That's not okay either. Okay, you are not going to learn it while you are getting the exam. I understood it because they are talking about the things that I didn't teach you in the class. Okay, and they are talking about much more complicated stuff that Wikipedia talks. I don't like that kind of a behavior. So we are having problems with around 20% of the people. The rest are giving me either no answers, like half the people, or the answer they think that they are right. So this is a class you are not supposed to know everything, okay? And we are trying to understand if you are getting what I am teaching you. It looks like most of you don't get what I am teaching you, or you are waiting until the midterm to study or something. So that's not a good way of learning stuff. You learn it from me, okay? You don't try to learn it just before the midterm exam or the final exam. Okay, that's some feedback for you. Okay, I will see you next week.
Sir, you uploaded the last day video, but it's April 6th lecture actually. I think there's a mismatch there in
Really?
YouTube channel.
Oh, that's bad because I raised. Okay, I need to look it up. I need to look it up. So I uploaded the wrong lecture, not yesterday's lecture.
Yeah.
Uh, so the title is wrong. Is title wrong too? What did I load it? Scheduling and schedule.
You uploaded the same video twice, sir.
I uploaded the same file twice. But YouTube. Okay, I will look into it. Thank you.